Let's begin this lesson by looking at something called a scientific method. What is a scientific method? Nothing difficult. A scientific method is simply a logical and orderly way to ask and answer questions or to solve a problem. And most scientific methods involve a series of very simple, very logical steps. The first step might be to figure out what the question is, or what is the problem you're trying to find an answer to, and state it in simple terms. The next step, do some research. You can't answer a question, you can't solve a problem unless you know something about that topic. And then construct a hypothesis. Come up with a plausible answer based on your research. What do you think the answer to the question or the problem is? Next step would be to design, set up, and do some type of experiment to test that hypothesis. Once you've done the experiment and you have some data or information, you need to look at it and analyze it. What does that data or information say about your hypothesis? And then draw a conclusion. And a conclusion is your answer based on the data from your experiment. Once you've done that, then you can run out and tell the world about what you found. In other words, communicate your results. Tell the world. With all of this in mind, let's look at a problem. Well, here's a problem, and this problem states, if a ball rolls down an inclined surface, what effect does the angle of the surface have on the average velocity of the ball? And now that we have this problem, let's just imagine for a moment that we handed this problem to a group of 10 students and said to these 10 imaginary students, take this problem, use the scientific method, and solve this problem. And that's where we are in this lesson, and that's what we're going to do. We're going to look at this problem. If a ball rolls down an inclined surface, what effect does the angle of the surface have on the average velocity of the ball? And we're going to look at how a group of 10 students, 10 imaginary students, might approach this problem, use the scientific method, and solve this problem. And in doing that, we will learn all about the scientific method and how to use it to solve our own problems. What did our 10 imaginary students do next? Well, they had a meeting. They got together and they looked at the problem. If a ball rolls down an inclined surface, what effect does the angle of the surface have on the average velocity of the ball? To help them answer that, they drew a simple diagram. You can see their diagram here. Table A and Table B. One end of Table B is lifted higher than the same end on Table A. That increases the angle on Table B. And they imagine that if they placed a ball on each table and let the ball roll down, that they could answer this question. What do you think will happen to the average velocity of a rolling ball as the height of one end of the table increases? And if you look at this and recognize it, this is the problem simplified in its simplest terms, written as a question. What do you think will happen to the average velocity of the rolling ball as the height of one end of the table increases? And they predicted an answer to that question before they ever let the ball roll down the table. They predicted an answer to the question, and the answer to this question becomes their hypothesis, their educated guess based on what they know, based on any research that they've done. What do they think the answer to this question is? What do you think will happen to the average velocity of the rolling ball as the height of one end of the table increases? And they answered it, if the height of one end of the table increases, then the average velocity of the rolling ball will increase. The hypothesis is the answer to the question or problem. And the hypothesis is written in if-then format. If one thing happens, then what happens because of that? If and then. So now they have a hypothesis. Now we can take a few minutes and talk about something called cause and effect. What is cause and effect? Well, it's an idea. It's a concept, but it is an extremely important concept because this is the concept that makes science work. The idea of cause and effect. This idea says that if anything happens, it happens for a reason. There's no magic. There's no luck. If something happens, it happens for a reason. And our 10 imaginary students used this idea of cause and effect, even if they didn't realize they did. Their problem says, if the height of one end of the table increases, then how does it affect the average velocity of the rolling ball? And our 10 students took that problem, simplified it, and then turned it into a hypothesis, an educated guess as to the answer to this problem. And their hypothesis was stated in if-then format. This if-then format simply means that if one thing happens, then something else will happen because of it. And it is actually cause and effect. If, then. If is the cause, and then is the effect. What this says is that if one thing happens, then something else will happen. In other words, this cause will produce this effect. If the height of the table increases, then the average velocity of the ball will also increase. What is it that causes the increase in the average velocity? It is the increase in table height. So now we're going to look at the relationship between two things. We're going to look at the relationship between two variables. We're going to look at the relationship between the cause variable, which is called the independent variable, and the effect variable, or the dependent variable. What's the real difference between them? Well, the dependent variable literally depends on the changing independent variable. If you look at this in terms of cause and effect, the independent variable is the cause, and the dependent variable is the effect that comes from that cause. So if and then, cause and effect, independent variable, a change in that causes a change in the dependent variable. And that's what we're looking at when we go from this point to design an experiment to test our hypothesis. We have to look at the cause and the effect, the independent and dependent variable. And so our 10 imaginary students are now at the point where they can design an experiment to test their hypothesis. And their experiment is designed to test the relationship between the table height, that's the independent variable, it's also the cause, and the average velocity of the rolling ball, and of course that's the dependent variable, and also it is the effect. So the entire experiment is going to be designed around this idea of cause and effect, because that helps us to identify the independent variable and the dependent variable, remembering that the dependent variable depends on changes that take place in the independent variable. When changes take place in the independent variable, they cause changes to happen in the dependent variable. You see, that's cause and effect. The students decided that they were going to work in groups of 2. The materials they said they needed: marbles or small rubber balls, all the same size and type, 1 per pair of students. A long table, such as a dining room table, 1 for each pair of students. Some books, bricks, and other objects to raise the height of one end of the table. A meter stick so that they can measure the length of the table and also the height of the table. And a stopwatch. Remember that they're calculating average velocity here, and average velocity is displacement divided by time. So they have to have some way to measure the time. They have to have some way to measure the time, and they have to have some way to measure the distance. Now, before we go any further, let's take a look up here where it talks about the materials that they need. And the first statement here says that they would need marbles or small rubber balls, all the same size and type, 1 per pair of students. Why do you suppose it is that the marbles or the rubber balls that they use will have to be all the same size and type. Well, I'll tell you, the reason is that if they're all the same size, then that keeps it constant through the experiment. And these items that you don't want to change from one part of the experiment to the other are referred to as constants. A constant is something that doesn't change. Variables change, and in this case there should only be two variables: the independent variable and the dependent variable. Independent variable and dependent variable. Those are the only two things that can change. The constants have to remain constant. So they want to use, throughout this experiment, the same size marbles if they're using marbles, or the same size rubber balls if they're using rubber balls. Nothing can change. And that also applies to things like the table. You wouldn't want one group of students using one kind of table and another group of students using a different kind of table. They have to be constant across the experiment. Why? Because the only change that you can have in this experiment is a changing independent variable, and that causes a change in the dependent variable. It causes an effect. So that's the way the experiment is set up. You have to think about these things all the time that you're setting up the experiment. When you're deciding what materials that you need, when you decide what you need, you have to make sure that it's all the same. And now our 10 imaginary students are at the point where they can write a procedure, a detailed step-by-step procedure for this experiment. And keep in mind all of the things that they have to look at. They have to look at independent variable and dependent variable and constants. So let's read down through it and see if they're paying attention to that. Step 1 says elevate one end of the table. The table elevation for each student will be different, and that is the independent variable, the different heights of the ends of the table. So let's see. Next it says, for instance, one group may elevate the table 10 centimeters, another group may elevate their table 20 centimeters, and one group may elevate their table 30 centimeters, and so on. Sounds good. Number 2 says mark a starting point on the table. It should be 2 meters from the lower end of the table. If the table is not long enough, then 1.5 meters can be used for this distance. It says the distance must be the same for each table, and that is a constant. That is a constant. It says record the distance on the data chart for all trials in the column labeled distance. So you know that we'll have to look at their data chart where they record information at some point in the future. And number 3 down here says practice letting the ball roll down the table from the starting line to the lower end of the table while your partner uses the stopwatch to measure the time it takes the ball to roll this distance. It says if you're good at it, your time measurements will be precise. Well, now remember, we talked about precision and accuracy, and it's always good to practice. You got to be good enough with the tools that you're using so that you don't negatively affect the accuracy or the precision of your measurements. So you have to practice with that stopwatch. It says once you feel confident that you can use the stopwatch precisely, then you can continue. And we'll come down to step 4 and see how they're doing here. It says set the ball or marble on the starting line and hold it in place by placing one finger on top of it. That's a good idea. You wouldn't want to give it a push one way or the other, and if you hold your finger on top of it, that's good thinking. Count, ready, set, go, and on go, release the ball or marble without giving it any push by simply lifting your finger as your partner starts the stopwatch. Start the stopwatch when the ball reaches the end of the table and starts to roll off. Step 5 says record the time on the data chart for trial 1, time. 6. Repeat steps 4 and 5 4 more times, each time recording the time on the data chart for trial numbers 2, 3, 4, and 5. Average the times that you recorded and enter the average on the data chart in the box labeled average. It says to do this you'll have to add the 5 recorded times and divide by 5. Seems pretty simple. Number 8, use the average time and the distance to calculate the average speed of the ball rolling down the table. And remember now, that average speed, that is going to be the dependent variable. And it even tells you here, record your average speed on the data chart where it says our average speed is. All right, our 10 imaginary students divided up into groups of 2. Each group had a table. One end of each table was lifted to a different height, and they rolled a ball down the table. They found the average velocity, and they recorded all of this information on a data chart. And here's the data chart where they collected all the information for each of the 5 groups. There's the 5 groups right there. Let's see, group 1, the average velocity that they calculated was 0.56 meters per second. Group 2, 0.34 meters per second. Group 3, 0.67 meters per second. Group 4, 0.25 meters per second. Group 5, 0.45 meters per second. So 5 groups, 5 different velocities, and 5 different table heights. You notice that each group has both a velocity and a table height, and it's different for each group. Also, keep this in mind. Don't forget, the average velocity, that is the dependent variable. It is also, in terms of when we talk about cause and effect, it is the effect. And the table height, you remember, is the independent variable, and it is also referred to as the cause. So if you change the table height, it causes a change in the average velocity. At least that's what you would imagine you would see. That's what your hypothesis says. So we're still working here with cause and effect, and this is the information that they collected. They collect information for the cause, the independent variable, and they collect information for the effect, the dependent variable. That's the only information they have to collect. Why? Because they're trying to test their hypothesis, and those are the 2 variables in the hypothesis, the cause and the effect, the if and the then, the independent variable and the dependent variable. And so our 10 imaginary students are at the point now where they can take the data that they collected and they can plot that data on a graph. And that's what we're going to do. We're going to look at their graph and see how well they did. See if they followed all the rules that are important to making a graph. The first one is a graph should have a title, and this one does. And this is a good title. What makes it a good title is it says dependent variable versus independent variable. In other words, average ball velocity, that's the dependent variable here, versus the independent variable, the table height. So we have the dependent variable versus the independent variable, table height. And that makes it a good title. It says exactly what the graph is about. What 2 things is it comparing? Average ball velocity, table height, dependent variable, and independent variable. All right, now let's go ahead and look at the x-axis down here. The x-axis is where you plot the independent variable, and you can see that they have plotted the independent variable here. It's table height, and they've also included right there the unit of measurement, the meter. You don't want to write down the table height without putting the meter next to it. In order to do this correctly, you have to include both table height, the independent variable, and the meter, the unit of measurement. All right, we'll come over here to the y-axis now. On the y-axis, looks pretty good. You can see what we have here. We have the dependent variable, and we also have right there the correct unit of measurement. The y-axis is where you plot the dependent variable, always. Dependent variable, y-axis, independent variable, x-axis. And now the next thing we have to do is we have to scale these axes. Let's see how they did. A lot of people think this is difficult, but it really isn't. All we have to do is come over here to the data, and we're going to look at the independent variable first because we're going to scale the x-axis first. And on the data, we see that the largest value we have for the table height is 0.24 meters. So we have to go from 0 right here over to 0.24 meters somewhere over here. We want to fill up as much of this axis as we can. And so what we did here, it looks like we counted by tens, and then we labeled each 10th line, and you don't have to label every single line here. That just makes a messy, hard to read graph. What you want to do is just label every other line or every 10th line or whatever value you're labeling with. So all you have to do is just label with every 10th line here rather than every single one. And let's see, that's labeled. Let's go over here to the y-axis now, and on the y-axis, if we look at the data, the largest value we have on the y-axis is 0.67. So we have to go from 0 up to 0.67. And if I went by tens, it would just run off. We'd run off the top of the graph. We'd never be able to fit everything in there. And I think if we went by fives, you just slightly exceed the length of this axis. So it looks like they went by fours here, which is good. They went 1, 2, 3, 4, and on that fourth line they put 0.1. That looks good. 1, 2, 3, 4, and then 0.2. And so they counted by fours over here, and then labeled it 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and 0.67. The highest one would be somewhere right up in here. So let's go ahead and plot the data points. So when we plot the data points, remembering each one of these is a coordinate pair. So over here we have 0.20 for the table height and 0.56 for the average velocity. So this coordinate pair is 0.20. We come up here 0.20, and we come over 0.56. There's 0.25, 0.55, and then 0.56 looks like it's somewhere right in here. So we come over here and we put that data point there. And then you notice what we do with this data point is we put a little circle around it. The data point is that. It is a point as small as you can make it, and then put a circle around it. So when somebody's looking for that data point, it covers up as little space as possible on the graph, and they can locate it because they know it's at the center of that circle. It has to be neat, very fine point, and then put the center of the circle there. And so we plotted here 5 data points. To recognize what type of pattern we have, all we have to do now is draw a line, and the type of line that we draw is called a best fit line. It is a line that shows the average position of these data points. So we would start down here and we would draw a line that showed just the average position of the data points. Does it actually have to cover every single data point? Absolutely not. It doesn't have to touch every single data point. It just has to show the average position of those data points, which looks to be right about there. And so there is our best fit line. What did I call that? A best fit line. It shows the average position of the data points. You know, there is some error. There's error in your measurements. There's always error in plotting points on a graph. But when you draw that best fit line, what you are looking to do is, again, increase your average accuracy. You're actually finding another average there, so you're increasing your average accuracy. And there is a good graph. Well, now we can stand back and we can look at the graph. We can look at the data in a visual perspective, and we can see that it looks to be a direct proportion between average ball velocity and the height of one end of the table. As the height of one end of the table is increased, the ball velocity appears to increase proportionally. That's what that straight diagonal line means. So now you have it. Now let's go ahead and review what you should understand from this lesson up to this point. Important things to remember. Science is based on the idea, the concept of cause and effect. It simply means if something happens, then it can make something else change or happen. Cause and effect, or if and then. The independent variable. You want to remember that the independent variable is the cause in any sequence of events. If the table is lifted on one end, then the ball velocity will increase. Cause and effect. The independent variable is the cause. The dependent variable is the effect. Also remember that when you state this as a hypothesis, that you can include the independent variable and the dependent variable, which in turn is the cause and the effect in that hypothesis. Our hypothesis today was if the angle of the ramp is increased, then the average velocity of a rolling ball will increase proportionally. We saw that that was a direct proportion, that straight diagonal line in the graph. Also remember that the cause is plotted on the x-axis, while the effect is going to be plotted on the y-axis of a graph. Other things to remember. The problem. When you're trying to state the problem, you can simplify it and write it in if-then format. Today, the hypothesis and the problem were very similar. The problem was if the height of one end of the table increases, then how does it affect the average velocity of a rolling ball? And if you look at the hypothesis, it also was written in if-then format. If the height of the table increases, then the average velocity of the rolling ball will increase proportionally. The problem and the hypothesis are closely tied together. Remember that once you write the problem, just turn it into an answer and state it in if-then format. When you're developing an experiment, when you're trying to figure out how to work this experiment, how to write the procedure, remember that the experiment is designed to test the relationship between the independent variable, in this case it was the table height, and the dependent variable, in this case it was the average velocity of the rolling ball. The experiment is designed to test the relationship between the independent variable, that is the cause, and the dependent variable, that is the effect. Keep that in mind. Also, when you're making a graph, label the axes and include the unit of measurement. In today's lesson, on the x-axis was table height in meters. You have to include the unit of measurement. The dependent variable was simply the ball velocity in meters per second. That meters per second is all important. You can't leave it out. Data points. Data points should be tiny points surrounded by a circle. There shouldn't be a big blob on a graph. The idea of that is that if somebody looks at that graph, they can know that somewhere in that circle is a tiny little point, and that point represents precisely, as precise as you can be, that coordinate pair. Best fit line. You don't want to have the line connect all the dots or all the data points on a graph like this. You don't want to do that. What you want to do is you want to include a best fit line, a line that shows the average position of the data points. Remember why you do that. That average line hopefully will increase the average accuracy of your graph. And then lastly, make sure that that best fit line is a straight line. Use a ruler. Well, that's what you should understand from this lesson.